You're listening to Wurth Elektronik's What's Up podcast, where we're seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts, including today's special guest, Valens Semiconductor, and our very own Wurth Elektronik technical specialist. We're going to be shining a light on some of our interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Wurth Elektronik's What's Up podcast. And welcome to today's episode, where we're going to be chatting about some interesting stuff in the world of electromagnetic compatibility and how to handle noise in electronic systems. EMI seems to be the repeat offender, and rightfully so. We're going to be going over a recent joint presentation with Valens Semiconductor that shares some practical insights into dealing with these challenges across different industries. So first up, we are talking about the flyback converter, which is often a noisy part of electronic circuits. We'll learn about some straightforward filtering methods that keep the noise in check and make sure everything lines up with EMC guidelines. This part gives a nice overview of how engineers can keep things running smoothly. And then in our second part, we'll move on to tackle the different kinds of noise that you might find in places like automotive, industrial, and medical settings. We'll point out some big EMI challenges in these areas and show a DSP-based solution that keeps data transmission solid even when the noise gets rough. And this is key for keeping everything working well in those tough environments. So stick around as we break down these topics, giving you a solid grasp on how to manage noise and meet those complicated EMC standards.
My name is Loran Völkel. I'm field application engineer at Wurth Elektronik, and I will try to show you something for passing the EMC test. Actually, when you are trying to do any data signals, transmission, receiving, whatever, every device needs to be powered somehow. So the power delivery means the power supply should be as well designed that you don't have conductor emission or radiator emission problem. The immunity mostly for a power supply is not a big issue. That's the part from Arno from Valens, because he will take care about the signal integrity, signal immunity in fact. So first of all, when you design a power supply, I guess the most simplest way to take it, if you have multiple input, or you have multiple voltage input, or you have your back boost conversion, sometimes a flyback is quite a typical, very easy design, especially when you make a galvanic separation, you can use a flyback topology. The flyback topology, we will look on that like a noise source, and we will try to make a design optimization, try to find out which kind of filter design and which filter step it will improve your EMI in terms of emission. After that, we will see what is the common mode and what is the differential mode noise, and then we have also the EMC lab results. In this schematic, I show you only just the input and output filtering. I take out of the IC part. So you can see here there are some jumpers. With these jumpers we can enable and disable the X capacitor, the Y cap. We can take out the common mode choke and put jumpers instead. We can take out the snubber. We can take out the jumper for primary to secondary ground, or primary hot to secondary ground, or primary plus to secondary plus, and try all these different capacitors to put step by step to see what means improvement in EMI, which each component give a better immunity, a better emission, or improve the EMC. So first of all, you will see here the board from 2022, because the first board what we did design for, I would say for education purpose, it was that we find out that there are some EMC fields below the filter. So electric field, magnetic fields, they are there, and we need to put some additional shielding. That was the reason why in 2023 we did redesign this board to be more efficient. This is on the bottom side, and on the top side you can see here there's a jumper parking space for no functional, just to put the jumpers in the right place. And then you see all these yellow jumpers are these step-by-step jumpers. We can take it in and out to see what is the impact of this difference without capacitor, with capacitor. And also the common mode choke can take it out and can put two jumpers to use it without any filter issue. So this is on the bottom side again. You can see we make a PE around the board, a nice good grounding, a lot of wires, using polygons of primary, secondary, and the idea was to achieve a good EMI and to be inside of the norm, to not make too much noise in conductor emission or radiator emission. So as first, when we go to the EMC lab after the board was designed, we take out all these different caps and we open all the connection. We just leave the flyback topology without input filtering and try to make measurement according to the 55032 quasi-peak and averaging standard. You can see this is the limits which you should not exceed, and as soon we switch on our power supply, we saw well, we have a little problem, so we can scream, Houston, we have a problem. Maybe we should try to sell it like a jammer. It would be a better idea instead of selling like a power supply. Yeah, we have to do something here. So first of all, we start with the snubber. The RCD snubber is something which every flyback topology need to put the snubber for the transformer, because you have a leakage inductance in the primary winding and you have to kill this leakage inductance for the next switching on. So the snubber, it make also something on your EMI. Sorry, that was too much. This is here. And the next step will be then to put this primary to secondary cap. So we put a primary Y cap for the primary plus to secondary ground, crossing the transformer, a kilovolt capacitor, maximum 1 nanofarad. And we saw already this capacitor. It helps. Anyhow, the transformer have a capacitor, but this is by accident. This is something which you cannot control. With this capacity, you can directly control this value. And then we saw, okay, the noise in the higher frequency already dropped. In this case, we start to do, okay, that looks, because this is a total conductor emission measurement from 150 kilohertz to 30 megahertz. It seems that it's more like a common mode noise. So we take a common mode choke and the Y caps for that, and as soon we place this common mode choke and activate the Y caps, we saw that everything above, I would say, 7-8 megahertz up to 30 megahertz is almost solved. The noise is dropping. It means that we saw that on the beginning, on the lower frequencies, just little improvement, even the impedance of the common mode choke was there. It means that this leakage inductance from the common mode choke acting also in the differential mode. So maybe we should add additional also the X capacitor, because we have also differential mode noise there. As soon we placed the X capacitor, everybody was happy, and we saw that the EMC requirement is CE plug. Can you put the stamp on it? It is required, it is okay. I was not that happy because the noise was much lower, but I was not happy because I always expect from everybody that when I help in the designs, I expect to have at least 10 dB distance to the limits. I know many people say I'm crazy, but I like to have this 10 dB distance because, you know, you have a tolerance between components as well. You have tolerance by the manufacturing anyway. And I will request always, if you are 10 dB below the limit, you're always safe. You never have be punished for any circumstances. Now we want to see what is this noise making. It is common mode or differential mode noise. So first of all, we will measure again common mode noise and conductor emission without any filter. So all this filter, we saw, okay, the noise is quite very high in common mode noise. So let's apply the snubber. The snubber makes some improvement, not that much. Put this primary to secondary capacitor. You can try out from ground to ground, primary to secondary, or plus to plus, or plus to ground. We found that the plus to ground capacitor was the best improvement. So we saw that in the high frequency already there is some improvement. In this case for common mode noise. Put the common mode choke with the activate with the Y caps. Then we saw, okay, the common choke, like expected, make this job, and we have a quite very nice rejection. We have a nice filtering. Everything looks fine. But we still have one capacitor to activate. This is the X capacitor. And look what happened in the low frequency, even for the common mode noise. When I activate the X capacitor makes this short on the noise level, so he turned back this noise to the flyback, and you don't have outside of this device anymore the common mode noise. Every common mode noise, somewhere it's happening in the loop where it's a differential noise, and if you can cancel that fast enough and close enough, then you will not have to fight again common mode noises. So this is in kind of common mode noise. If we look now to the differential mode noise, in differential mode noise we saw that the noise was much more less like in common mode, and yeah, in differential mode noise I think we don't need to optimize anything. We have more like enough distance to the levels, and we still need to improve the design. So we start to redesign it after we find out that with the near field probes, if you go close to this area, you will find out some electrical fields and some other loops, which is magnetic fields. So that was the reason why we start to redesign the board, make a new PCB, keeping the same BOM, keeping the same components, just replacing the PCB to still 2 layers, but change the idea how to make this layouting, because by layouting you can improve a lot sometimes if you know exactly where the noise are running. So look, you see here the schematic. What he did get additionally is just some measurement points. We put some SMB connector that we can make directly measurement to the input and output, and also for the stability we can do something, and that's the only one thing what we put additional some SMB connectors. But the layout changed dramatically. You can see now that we don't have anymore this frame for the PE, for the protecting earth. We just have on one side, we change a little bit the polygons, we make it more shorter, and try to eliminate this every parasitic inductance and capacitive coupling. You can see now this SMB connectors here, and also the extremely good grounding for the Y caps to have no additional parasitics for the capacitors. This is on the top side. Now we'll show now the bottom side. Again, you can see this PE line and extremely good connection to the ground layer with the additional steel spacer connection, not only just by via additional steel spacer, also to ground. So actually should be an extremely good connection, low impedance connection, and also the position of the capacitor of this filter capacitor around the IC getting more closer like in the design before. After the board was done in the redesign 2023, we go back again to the EMC lab, because the EMC lab has this kind of lying detector. It calls also EMI receiver, and the EMI receiver start to measure, and then first measurement like before without no filter improvement, so no filter at all. We saw that the noise is still high like before. So this layout or change, this rerouting and remanage the layout, it doesn't manage anything on the noise level. So again, put first the snubber on, the snubber, like before, not a big improvement, almost the same frequency. Put this primary to secondary cap, and then we start to sweat a little bit, because we saw that in the design before, in the 2022 design, this transfer capacity primary secondary, it doesn't matter how we try to manage that, it was much more effective. So maybe our redesign was not the best what we should do. But let's put now the common mode choke and the Y caps on, and as soon we put the common mode choke and the Y caps, we found out, okay, that have a much better impact like before. Now we see that the noise is in the higher frequency, above 5 megahertz, starting to get very, very low, and we have more distance. So the next step, it is just to apply also the X capacitor, and this is the final measurement, because this is the total conductor emission. And the final measurement we saw, wonderful. This is exactly what I am expecting. The green line, it is when you have no common mode noise, no differential noise, and you have more, like we say, more than you expect, distance and to level, and if you have more like 10 dB, I guess every EMC lab, the design and the measurement engineer will come to you and offer you a coffee, because this is very rare. It's not always a day, every day is happening that you have such low noise level when you put all the filter on. So now again, we want to find out what is common mode and what is differential mode. So in a common mode measurement, only just measuring with a listen, the common mode noise without any filter. We know we have the noise there. Put on the snubber like before, we didn't have a big impact. Put this primary to secondary cap. We saw that in a common mode noise there is an improvement. And this time the improvement is then maybe not that much like before, but it takes improvement anyway, same value. And after we put the common mode and differential common mode and the Y caps, only the common mode and the Y caps, we saw that the effect of this filtering is extremely good. Even in the low frequency is not enough. After we put the X capacitor, we saw that we have more like 10 dB space to the limits. So in the common mode measurement, it's quite extremely good. So the total emission was also good. That's something which you should be proud if you design something. And when we switch to the differential mode measurement, in this time, when you get this low level with the green line, focus on the EMC measurement engineer. Look to the EMC guy, because he will be impressed. He will congratulate to you, and he will check first if his machinery is really working. Because when you have these low limits, low peaks about just the noise floor, he starts to be afraid that he didn't measure something correct. He's not connected the antenna or something, because this is very, very rare. When you reach this level, some EMC guys even that print it out in the A3 format and put to the chamber and say, look, it's also possible. Try to achieve this measurement, because this is something very rare. But okay, that was the intention, to have a good EMI, and that was possible because we tried to read these books. I can offer to you some idea. We have nice books about trilogy of magnetics, connectors, also for LT spice, also for connectors and capacitors. You can ask my colleague in the sales if you want to have more information about EMI and about components. I just can invite you to read these books. And if you do a own small lab and you want to make a own setup, we can help you also with some lab racks. You can have all the different components like common mode choke and chip bit ferrites and capacitor. Depends how big is your lab. You can have that on wall, or you can have that on your table, or such racks. Just ask my colleagues from the sales, and they will help you to guide you to find the right EMC lab rack for you. If you want to find out more about how components are measured, we have also a YouTube channel. If you go to YouTube and type in a hashtag #AskLaurent, you will find more like 200 videos with some jokes and also some measurements in our lab. And I invite you to find some interesting point for your design as well.
So, welcome to my presentation. My name is Arno Distel. I'm a field application engineer at Valens Semiconductor. I want to talk to you today about these topics. First, I want to introduce the company Valens Semiconductor in a short way. Then I will show you some specialities about the different EMC noise profiles in the automotive industry. I will follow the chapter with EMC challenges in industrial, and talking afterwards about DSP-based approach to EMI, how to solve the issues which are present with electromagnetic noise being influencing data transmission. And finally, I will talk and show you a challenge in the medical industry in terms of EMI. Valens Semiconductor is a fabless semiconductor company. We are focusing on wired transmission of high-speed data transmission, though high bandwidth in the range of multi-gigabit links. We try to reach the longest physically possible cable length, and at the same time reach a lowest possible error rate for enabling our systems also to be applied into safety critical applications. We are active in different markets. Our roots are in the professional audio-video industry, where we have significantly contributed to the HDBaseT standard, the industry standard to transmit multi-gigabit video data. And since quite some years, we are also successful in industrial, automotive, and medical markets. And as a second industry standard, we are contributing to the MIPI Alliance physical layer APHI, where this is also serializer, deserializer combination for transmitting of video data from optical sensors, radars, and LiDARs. I will focus on these three industries today and show you various EMC challenges across this. Let's start with the EMC challenges in automotive. I want to highlight the 4 different main noise types which are existing in the automotive applications, or which cause troubles designing applications. The first one is additive white Gaussian noise. Additive because it is superimposed to the wanted signal. White, it's evenly broadband, evenly distributed over a frequency range, as similar as white light. Then Gaussian, we need to have a look into the distribution of the peaks. This means the higher the amplitude of the noise gets, the less likelihood it is to occur. Though this all means it is the higher the energy of the noise is, the less it is occurring. So this is quite easy to handle. There's also the second type of noise is transients online. I'm not talking about the voltage supply lines in a car. I'm talking about the data lines. But these transients are induced into the data lines by all kind of electrical systems within the vehicle, which are switching power, switching currents, and these transients occur with quite very high amplitudes, but luckily with a short duration of several hundred nanoseconds. So also we can handle that. The third type is alien crosstalk from different cables in the vicinity. You need to imagine a car like a Golf class is having 1 to 2 kilometers of cable in it, and the upper class with full rolled out functionalities can have up to 8 kilometers of cable. And so you can imagine there's a lot of possibilities to coupling between to couple noise between several cables which are running in parallel over a certain length. The last noise type, in our opinion, the most critical one, is the narrowband interference caused by radio frequency applications, for example, external to the vehicle transmitters, or also handheld devices brought in to the car by the driver or passengers, like a smartphone, which is used inside the car. And when the car is on the road, the smartphones are continuously registering into the next cell. So there's continuous radio frequency transmissions, and this is causing interference in the cables of the car, and so in the signal transmission. How do these noise profiles look like in time and frequency domain? Let's first have a look into the time domain view. You can see on the left side, there's the blue is the transmitted signal, the wanted signal, as it is coming out of the transmitter. And afterwards, the orange part in comparison is the signal as it is received on the receiving side. You can see there's a certain loss of level caused by the damping on the cable, on the transmission. And compared to these, we have the 4 types I've talked about. The yellow one, the narrowband interference with also quite a high amplitude, and the crosstalk, the white Gaussian noise next to that, and you can see in green the transients online with a quite huge voltage spike, but also very short duration of time. When having a look in the frequency domain, we can see in the same colors the TX signal coming out of the transmitter and the orange signal as it is received after the channel. You can see the frequency dependent attenuation. The higher the frequency gets, the bigger the attenuation gets. And we can also see, as described, the crosstalk, car noise and transients are well below that in terms of the spectral density. And I'm not sure if you can see it properly, the yellow short line, the narrowband interference narrow in the frequency domain, but you can see it has quite high power spectral density even above the wanted signal. What are usual legacy EMI countermeasures? We can limit the cable length and we can reduce the bandwidth. Limiting cable lengths, of course, giving the system less possibility to induce unwanted noises. And reducing the bandwidth will close the opening bandwidth of the receiver, which of course also doesn't amplify noise in a higher way. But this of course imposes a lot of limitations on the system design, which is in the most cases not possible. We can apply shielded cables to keep out the noise and to work with the shield damping. But the shielded cable, these will degrade over lifetime. You can imagine when you have a camera mounted on in the mirrors of the car and the cable is fed through the door. When the driver enters the car, he's opening the door, closing it, and after reaching the destination, getting out of the car, opening the door, closing it. So you have 4 times already per single ride where the shield is bended. And this over a lifetime can degrade significantly the shielding and also the insertion loss of the cable. Finally, we can introduce forward error correction. We could add redundancy to the signal which is transmitted. This is working well for the receiver to detect errors and to correct them. It is working well as long as the signal-noise ratio is high enough. When the signal-noise ratio is getting worse because the narrowband interference is present all the time, we have a lot of high probability of the radio emissions. And so this would mean we would need to add more and more redundancy to compensate. And this has a severe impact on the possible data throughput. And how these effects or how these countermeasures are working, we can show. I want to show you in a video where we took a series car with the ADAS system and put antenna close to the cameras with a very limited signal amplitude of minus 13 dBm, and we will see the impact what it has on the ADAS system.
In this video, we will demonstrate an example of this vulnerability using a signal generator to inject electromagnetic noise into an ADAS system at levels far below the industry standard. As you can see with the introduction of the noise, the video from the far right fender camera flickers and ultimately fails. In our second scenario, we conducted the same sweep as in the previous one to demonstrate how the autonomous system functions both before and after noise is applied to the trifocal camera. During the normal operation of the car, the system picks up the movements of pedestrians walking by, as well as other cars. However, as you can see at the bottom of the screen, after the application of the noise, the autopilot system completely malfunctions, failing to identify both the pedestrian and the car. In this case, the driver assistance system entered initial calibration mode, requiring a 30 to 40 kilometer drive to recalibrate, during which time the cameras were not functioning. It's important to note that the noises being applied here are noises that could occur on the road.
So let's go to the next chapter, having a look in industrial applications. Of course, here the noise profiles are quite similar. We have also wide broadband Gaussian noise, and we have also some RF applications which are creating narrowband interferences. But we have some challenge which makes it quite special. In terms of cable length, often longer cable reach needs to be applied compared to the automotive industry. So this can reach even 100 meters or beyond for industrial applications, which mean even more noise can be induced into the cable, and a cable length reduction is not a countermeasure which is possible to go with. And together with this, the longer the cable gets, the more attenuation it has on high frequencies. So when having a look at the insertion loss here in this graph, you can see the comparison between a 2 meters coax cable and the 15 meters coax cable. And when having a look at a data transmission, which is working at 1 gigahertz Nyquist frequency, we have a gap of 9 dB reduction in damping of 9 dB higher damping. And when going to 4 gigahertz transmission, for example, we have even close to 22 dBs. So this means the higher the frequency gets, and the higher the longer the cable gets, it is even getting more and more challenging to get the system working. A second challenge in this industry is the demand of flexibility. So similar like the example with the doors feeding through a wire. Here in this case, the picture of the industrial robot requires flexibility in all dimensions, and this means often it's required to use unshielded channels which offer higher flexibility. So this countermeasure of using shield is often not possible as well. But are there alternatives? Yes, there is. We can apply a DSP-based approach into the receiver to compensate the issues which are occurring due to the noise present. In this example, I want to show you the MIPI Alliance AFI standard-based approach, and this is present in the chipsets from Valens which are compliant to this AFI standard. The first method is using a pulse amplitude modulation for the transmission, which means we are transmitting more bits per symbol, leading to a lower frequency on the cable. For example, with a PAM16, we can transmit 4 bits per symbol, and when you have a look at the graph on the right bottom side, there's the PAM16 with it running, for example, with 8 gigabit per second data throughput. We can run that over a transmission frequency of 1 gigahertz. The second method is adaptive equalization, which is adjusting in real time, compensating difficulties in the transmission channel. This can equalize variations of the channel and can also compensate reflections, what you might have during a cable structure with inline connectors or connectors which have not a steady impedance over the link. We can see in the graph there's in front of the equalizer we have scattered data points having different voltage levels, and the equalizer is adapting to this to make out of that 4 distinct voltage levels, which in this case, in this example, it's a PAM4 modulation. Now I talked about the narrowband interferences, and as soon as these are attacking, the well equalized signal gets distorted, as you can see here in the picture, and this is the reason for the third method applied into this design, which is noise cancelling these EMI attacks. And you can see there's a short learning period of around about 1 microsecond, where the noise canceller is adapting to the situation, and afterwards it is again the clear distinguishing between the 4 voltage levels in the case of PAM4. And finally, we have a dynamic error correction, a retransmission method, where you can see one original packet is having errors due to the noise present, and this is detected over a checksum or over a message counter. If it's a completely lost packet, the receiver can detect this. He can or ask for retransmission of the packet, and the packet is sent again. And all this happens within 10 microsecond latency, because this is implied in the physical level of the transmission. And how these methods are working in competing to legacy solutions, Valens Semiconductor did a live demo at the CES in 24, and I have a video where you can see the comparison between A-PHY standard compatible 8 gigabit per second transmission versus a proprietary ZS solution with 6 gigabit per second.
Here we have our transmitters. One is the Valens VA7000 series running at 8 gigabits per second. The other is a competing legacy solution running at 6 gigabits per second. Both are connected with identical cables up to their respective receivers. We've attached a signal generator that injects noise into the links to test the robustness of the receivers. The images are shown on the screen. On the left side, you see the competition. On the right, Valens A-PHY compliant chipsets. Let's start with the competing solution, starting at minus 14 dBm and working our way up. As you can see, at just minus 13 dBm, this solution fails to withstand the noise, while the Valens VA7000 chipsets continue to withstand the injected noise. Let's crank it up to 0 dBm, 10 dBm. It's still working. Finally, at plus 14 dBm, the link fails.
This means 20 times higher noise robustness regarding the competing system. Now let's go to the last chapter of my presentation, which shows an EMI challenge in medical. I wanted to introduce to you to electrosurgery, where you can see here in the operating theater, the patient is lying on the operation desk. There's a dispersive electrode attached to the body, which is connected to the electrosurgical unit. And the surgeon has an active electrode in his hand to cut tissue or to coagulate tissue. And this can be also used during endoscopy, where the active electrode is operated remotely. And there's different profiles of current used in this procedure. There's a cutting current with a continuous waveform, and there's a coagulation current with a modulated waveform. The frequencies usually are in a couple of hundred kilohertz up to 2 megahertz. That's well above the frequency where neuromuscular activity is induced. And there's also blended current, which is a mixture of these modulations. And especially when this is used during endoscopy, there's a coupling between both cables, which are lying in parallel inside the endoscope. You can see here the black one is the cable used for powering the electrosurgical equipment, and the blue one is the cable which is powering the camera and also the LED light, and which is also transmitting the high-resolution video here in this case with 4K 60 frames per second. And we can I can show you a demonstration inside the video how this setup is working with the noise canceller enabled and with the noise canceller turned off.
The sensor data is driven from the tip of the scope using the Valens VA7031 serializer over a very thin and flexible 5-meter coax cable. On the receiving end, the Valens VA7044 deserializer is connected to the NVIDIA Orin processor that displays the 4K video. Solutions on the market today using only forward error correction or no correction methods at all cannot handle the electrosurgical procedure interference. We simulate this by running the setup with the VA7000 noise canceller disabled. Turning on the noise generator to a level of just 10 watts and using the probe on a lemon simulating a patient, the link fails and the video freezes. Now let's repeat the process, but this time turning on the Valens VA7000's built-in electrosurgical noise canceller. As you can see, the video remains picture perfect at the same level of 10 watts. We can do it again, turning the noise higher, and again, the video remains uninterrupted.
Thanks for tuning in to today's episode, and if you're looking for more EMC solutions, be sure to check out the Wurth Elektronik website at www.we-online.com. Now, we understand that some pictures and videos might not be available on all streaming platforms, so we encourage you to watch the full presentation and download the slides on our Wurth Elektronik Group YouTube page. And don't forget, Wurth Elektronik offers a wide range of components to complete your applications, including connectors, power magnetics, optoelectronics, and so much more. You can find all of these on our website as well. You're listening to Wurth Elektronik's What's Up podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast.